Welcome to class 10. In this class, I'm going to just work end of chapter problems. And I also, not as part of this class, but in a separate recording, plan to work some homework problems. So be looking for those as well. We're going to start with problem 5.8. This problem is a little bit unusual in that it's looking at all of these past costs. And one of the things I usually tell my class early in the semester is that engineering economics is usually concerned, in fact 99% of the time, with decisions about the future, not looking at the past. But in this case, this problem does look at the past, and it asks us to accumulate what is the annual cost over the past 9 years for some equipment. So let's read the question and then look at what the data is given and what they're asking for, as we usually do with these problems. The question says White Oak Properties builds strip shopping centers and small malls. The company plans to replace its refrigeration, cooking, heating, ventilation, and air conditioning and other equipment with new models in the entire center built 9 years ago. So this center was built 9 years ago, and they're going to replace all the equipment. The original purchase price of the equipment was $638,000 9 years ago. Okay, so that was a present value 9 years ago. And the operating cost has averaged $241,000 per year. So this is a P 9 years ago, and this is an A over the last 9 years. Years minus 9 through the present. Okay, determine the equivalent annual cost of the installed equipment if the company can now sell it for $184,000. The company's MAR is 25%. So let's draw up a cash flow diagram, and we'll let 9 years ago essentially be the present time. So if that was the case, that was time zero is really kind of 9 years ago. Then we spent at that time $638,000 to buy this equipment. So that was a minus 600. And then we had a uniform series of 240 a year for those 9 years. So this is a uniform series that went on for the 9-year period of 240,000 minus 240. And now he's saying we can get 184,000. This is the market value right now at time 9 of this equipment. So that is a plus $184,000 salvage value or market value, or another way to put it is it's the future value, but it's now, future being from 9 years ago. And we also have a MAR of 25% per year, and it's assumed to be compounded annually. So that's our cash flow. And the author is saying, what is the equivalent annual cost? So how do you convert all of this into a uniform annual series? So we're going to take each of the elements of the cash flow and make it into a uniform annual series over this period of time. So I'll say the annual equivalent, annual worth, annual cost, whatever you want to call it. Really, this is an annual cost at 25% of this cash flow. So I'm going to start with this one. that's a present value. To make that into a uniform series, that's A given P, right? So this is minus 638,000. A given P, 25% for 9 years. And then I want to make this into a uniform series. Well, it already is a uniform series, so that's just minus 240,000. This uniform series is over years 1 through 9, as I've numbered them at least. This is 8 and this is 9. And then this uniform series is over years 1 through 9. Then I have this salvage value of plus 184,000. Well, that's a future value relative to this time frame. So I'm going to say that's 184,000. And I'm going to convert that to a uniform series, A given F, 25% for 9 periods. So that is the equation that gives me the present value of this series. I'm sorry, the uniform equivalent of this series. And I'm going to then break this down for a minute, because in this chapter the author talks about the annual cost of capital recovery and the annual cost of operations. Well, the annual cost. So let me look at this in as the following. This is the annual cost of capital recovery at rate I, which is 25%. And plus the annual cost of operations, AOC, and that's also at 25%, but the 25% really doesn't come in because that cost, that annual operating cost, is given as a uniform annual series, so we don't have to do anything with the interest rates. So your annual cost of capital recovery, ACR, or CR, period CR, at 25% is the price in the salvage value, those two items. So this would be this minus 638,000 and this plus, okay? So this is minus 638, A given P, 25% in 9 years, plus 184,000, A given F, 25% in 9 years. So the capital recovery annual cost is these two parts. This is an operating annual cost. So I could have just solved this equation, but I'm going to break it into two parts, get the capital recovery and the operating. So we can kind of keep those two things separate. Well, when I multiply this times this, I can use my app, and if I do, I'm going to get $184,226. That's dollars per year for 9 years. And then I'm going to take this and bring it back at 25% for 9 years. That's A given F. And when I do that, I'll get $7,131, and that's dollars per year for 9 years. And then I can add those two. This is a minus sign, sorry, because, I'm sorry, it is a plus sign. It's a plus sign. So when I add this to this negative, I get equal to minus $177,095. Okay, because that's a positive salvage value, that's a negative cost. That's the cost of capital recovery at 25%. And then I'm just going to add the annual operating cost and the minus 240 to that to get my final answer. So AC at 25%, the annual cost at 25% is this number minus $177,095 per year for 9 years, minus 240,000, per year for 9 years. Since those are both over the same time frame, I can add them, subtract them, whatever. And then if you do that, you'll get minus $417.95. And so that's the solution to problem 5.8 at the end of the chapter. And I'll go on to the next problem. Okay, the next problem I'm going to work is problem 16 at the end of chapter 5. So let's read the problem and see if we can set it up according to the data given. City Council of a southwestern city is considering the construction of permanent restrooms in 22 of its smaller parks, that is, parks less than 12 acres, or pay for portable toilets on a year-round basis. The cost of constructing the 22 permanent restrooms will be $3.8 million. The 22 portable restrooms can be rented for $7,500 each year. Each the first year, 22 portable restrooms for $7,500 each the first year, with rental cost increases of $25 per portable per year, for a maximum contract period of 10 years. The service life of the portables you can get a 10-year contract on, okay? The service life of the permanent restrooms is 20 years. Using an interest rate of 6% per year and an annual worth analysis, determine if the city should build the permanent restrooms or lease the portable restrooms. Well, we have some decisions to make because one issue is, what is the study period? And since the permanent restrooms will last 20 years and the contract for the portable restrooms will only last 10 years, this problem really should state what the study period method should be. And I'm going to say use the least LCM, least common multiple of lives method. Now, I think what we want to do is assume that unless the author tells you the study period is something different than that. And, for example, he could have said, the author, that the study period is 10 years. If he would have, then he would have had to give you a salvage value for these permanent restrooms at the end of 10 years, because they really will last 20 years. And so he didn't give us a salvage value at the end of 10 years. He didn't tell us what the study period was. So we have to assume least common multiple of lives. That's an important fact because you have to know what your end value is going to be. Now, so I'm going to break this problem down, the problem data, into two parts. We're going to have the build option. The build option, you have, if you do that, you have a present cost of $3.8 million, which I'm going to write out the number, minus 3.8 million is 3,800,000. And then you have that is for n equals 20 years. On the other hand, you have the rent option, and that is going to be $7,500 per year per porta potty, okay? And there's 22 of them that are needed, so that'll be times 22, which is $165,000 per year. That's in year one. And then he says they go up by $25 a year. So they're going up by a constant amount, okay? Going up by a constant. So that's going to make us into a G series, capital G. That stands for an arithmetic gradient of $25 per porta potty times 22 porta potties, which is $550 per year. So that is the option of renting. Now, normally rent is paid at the beginning of a period, just like if you rent an apartment or whatever, you generally pay the rent at the beginning of the period, but we're going to assume end of period because these could be monthly payments, and the payments made during a year are placed at the end of the year. So we're going to assume these are all placed at the end of the year. So basically, if we draw a cash flow diagram of this, we're going to have minus $3.8 million, 3,800,000, and that's going to cover us for the entire 20-year period. That's it. This is the only cash flow that works for 20 years. Now this cash flow, the first year is going to be minus $165,000, and we'll just put it at the end of the year. Put a little squiggly there because that's not to scale. That's in year one, and then each year after that, it increases by 2 up through 10. It increases by $550 a year. Okay, this is a minus 365, and that's going to be an additional minus 550 each year going up. So that's a geometric gradient. Of course, this 10th year, it'll be quite a bit more than that. It would be 9 times 550 plus 365. We don't have to figure out how much it is because our factors will take care of that. Now the problem is we've got a 10-year series here and a 20-year series over here. So we have to assume this series repeats. Well, I'll tell you, this is a really strange assumption because remember, this cost was going up, but we don't know any different that they couldn't sign another contract for another 10 years that would start back at $165,000 the first year and go up. So that's what we're going to assume. And we already know that if we assume that if we get the annual cost for the first 10 years, the annual cost for the second 10 years be the exact same as long as the series repeats itself exactly, which is what we assume when we use the least common multiple of lives, which in this case is 20 years. So what I'm going to do is find the annual cost of this over 20 years, the annual cost of this over 10, and assume it's the same for the entire 20, and then I'll look and see which one is lower and select the lower cost alternative. The author tells us the interest rate is 6%, and usually when you're dealing with government type projects, the interest rates are much, much lower because the government can borrow money at lower rates than private industry can borrow money, generally speaking. At least the U.S. government can, and so that leads into that lower interest rate. So the next thing I'm going to do then is convert this to a uniform series, and I'm going to call that the annual worth at 6% of the build option. Okay, so I subscripted that with a B, and that would be simply the present cost minus 3.8 million 3,800,000, A given P, 6% for 20 years. Let me continue my break between these two. And then I'm going to get the annualized value of this. Well, the minus 165,000 is a uniform series. If I cut off these arrows, then I just have to annualize this gradient series that's left, okay, the arithmetic gradient. So the annual worth at 6% of the rent option is going to be minus 165,000. That's dollars per year for 10 years. And we're going to assume then it can be repeated in the next 10 years. Minus 550, that's the G series, A given G at 6% for 10 years. And if you calculate this out, this turns out to be minus 165,000, and this is a minus 212 2,212, and so that will be minus 167,212 So that's the annual worth of renting at 6% interest and 10 years, but we're going to assume then it's for 20 years. So this is for years 1 through 20, because this is the first cycle cost, and the first cycle cost equals the second cycle cost, and that's what we assume, and so that's it. Now this number here, when I compute that out, this is going to be for 20 years, and this is minus $331,000 and 301, and so this is going to be dollars per year for years 1 through 20. So this is years 1 through 20, this is years. I can compare these two, and certainly renting is much, much less expensive. So that's the end of this problem, and I'll work another problem for you next. Okay, the next problem we're going to work is problem 27 in chapter 5 that states a new bridge across the Allegheny River in Pittsburgh is expected to be permanent and will have an initial cost of $30 million. This bridge must be resurfaced every 5 years at a cost of $1 million. So after 5 years, they're going to have to resurface it. Then again after 10, 15, and so on for as long as the bridge is there. The annual inspection and operating costs are estimated to be $50,000 a year. So this is an annual series. Determine its equivalent annual cost of this long life construction at 10% per year. So we have an interest rate. This is a key term here, long life, because he's asking you, let n approach infinity, okay? Or he's telling you to do that. So we have a present cost which is going to be spread over an infinite number of years, of $30 million. So P is equal to 30 million. Then let's draw this up so we can kind of visualize it. It always helps. I'm going to go through what we're given. The 30 million is here. Then every 5 years, it's going to be resurfaced at 1 million. So we got 1, 2, 3, 4, 5. You got 1 million. And then that happens again at 10, 1 million. And so on, all the way out as n approaches infinity, okay? And then you have operating and inspection costs, those kind of things, of $50,000 a year every year. So that continues on like that. And it goes on as n approaches infinity. That's 50,000 minus. That is a uniform series, and these are all negative. So everything is negative. So the annual worth now is what the author's looking for. So annual worth at 10% of this cash flow. Well, we have a present value there. That's minus 30 million. And we can spread that forward. A given P, 10% for n approaching infinity. And then we have this $1 million every 5 years for resurfacing. Well, I'm going to spread this first $1 million over the first 5 years, and then take the second 1 million and spread it over the second 5 years. Well, that's going to be the same spread. So this, once I spread this one, it's going to go on for infinity. So this is minus 1 million A given F at 10% for 5 years, and that continues on forever. So that's going to produce an infinite uniform series, and then you also have the minus 50,000, which is an infinite uniform series by itself. These now, this is per year forever. This is per year forever. This is per year forever, so to speak. And then so that is the thing we're looking for at 10%. Well, what happens to A given P when n goes to infinity? We know from our equation for capitalized cost that goes to 1 over I. I'm sorry, that goes to I. The opposite would be capitalized cost. This is the capitalized cost here. And to make that into an A series, we simply multiply that times I. So if you look at this equation, the limit as n goes to infinity of that algebraic equation is simply I. So this 30 million then times 10% will be 3 million, okay? So that's minus 3 million. And then this is times A given F, 10% for 5 years. So this will be, if you compute this quantity here using your app, you're going to get, let's see, minus 163,000 and 797, and then you have added to that a minus 50,000. That's this number. And you then add all of those together, and you're going to get minus 3,213,797. Now, I looked this up on the answer key, and I did this with all of these problems that I'm working here in Chapter 5. The author uses the equations in the back of the book. I'm sorry, the tables in the back of the book, and the app is actually carries more decimal places, so it's a more accurate answer. And the equations in the back of the book give you minus 3,213,800, difference of only $3, and that's going to give you the correct answer. By the way, the authors considers an answer correct if it's within plus or minus 2% of the actual value. In several of these problems, like I said, I got a number that's different from the answer key. For example, again, if I go back to problem 16, which we solved before, and I use the author's answer, the author's answer is 167,212. Actually, that's exactly what I got using the app. So it works out good on that one. And so these answers might be slightly different, so I give you the answer key answer as well in the problem. So we're going to go on to the next problem. Okay, the last problem I'm going to work for you in this essential problem session, which is class 10, deals with, there's two parts, A and B, and the author wants you to use spreadsheets to solve problem B, but I'm going to show you how to work it without a spreadsheet, in fact. The first part, though, part A, for the cash flows shown, use an annual worth comparison and a MAR of 10% to determine the following: the alternative that is economically best. So what we're looking for is, of these three alternatives, X, Y, and Z, we want the one with the least annual cost. This alternative lasts 3 years, so we're going to have to assume least common multiple of lives, and that it can be repeated infinitely because this alternative lasts forever. And this alternative, Y, lasts 10 years. So we're going to assume it repeats every 10 years, this repeats every 3 years, and this goes on forever. So we're going to find the annual worth of each of these three alternatives and compare them over essentially an infinite time frame, because this is infinite here. So what's the annual worth of X? Let's look at that. The annual worth of X, well, let's draw the cash flow diagram of X first. And maybe I'll separate this. How do I want to do it? I'll look at it like this. Let's look at X first. X has a first cost of $90,000, an annual cost per year of $40,000, and a salvage value of $7,000. And that series will repeat itself every 3 years. So we're going to have a cash flow that looks like this: minus 90,000, 1, 2, 3, 40,000 a year, $7,000 salvage value. That's positive. And that series is then going to repeat itself every 3 years. And so if I find the annual worth of the first 3 years, it'll be the same forever. So the annual worth of x at 10% will be minus 90,000 a given p, because that's a present time, 10% for 3 years. The minus 40,000, and I need to put the sign there, is an annual series, so I don't have to multiply that times anything, just add it in, so to speak. And then I have a plus 7,000 sitting out here. That's a future value, and that's a plus value, plus 7,000 a given f, 10% for 3 years. So that's spreading this thing back, and this one here is spreading this thing forward. So all of these now are uniform series for 3 years. And if I compute this out, I got $74,075. That's the annual worth of X at 10%. That's really for years 1 through 3, but since the series repeats, it's really forever. Dollars per year forever. So that takes care of X. The next thing I want to do is look at Y. The initial cost of Y is 400,000. And that lasts for 10 years, so I'll have 1, 2, 3, and so on. Up to 10. And then we have 20,000 a year annual costs, so that occurs every year for the 10 years. So that is a uniform series. And then lastly, we have a salvage value of 25,000. That's a plus, and it's a future value. And that's the cash flow then for Y. And then so I'm going to say the annual worth of Y at 10% will be equal to minus 400,000 A given P, 10% for 10 years. And then I have a minus 20,000, which is an A series. So I'll just put that down. And then I have a plus 25,000, which is a future value, which is the market value of this equipment or whatever it is at the end of 10 years. So that's going to be A given F, 10% for 10 years. And if I compute this value out for Y, the annual worth of Y at 10%, this turns out to be 83,531. And this is going to be dollars per year for 10 years, but we're going to assume that this cycle repeats forever. So this is dollars per year forever as well. So when we compare this to this, we'd rather do X than Y, but we haven't looked at Z yet. So let's do that. If we look at Z, we're going to get minus 650,000 at time 0. 650,000. And this is going to go on towards infinity. And then 13,000 a year, that's going to happen every year as we go along. So I'll put a, and then 80,000 overhaul at the end of 10 years. So let's make ourselves a 10-year period here. This is year 1, 2, 3, and this goes to 10, and you have this minus 13,000 every year. And then in year 10, you have an additional minus 80,000. Oh, sorry. Okay, there we are. And then a salvage value at 200,000, and I assume that's at time infinity. Well, if something is worth 200,000 at time infinity, it's worth nothing for per year, because you're spreading it over an infinite number of years. So 200,000 is basically going to be divided by an infinite number to spread it out over an infinite number of years. So it's going to be 0. But so let's look at all of what we have here. We have this that this 650,000 we're going to spread over an infinite time frame, and we know how to do that. That's just going to be multiplying it times I. Okay. So the annual worth at 10% will be equal to minus 650,000 A given P 10% for infinity. Then you have this minus 13,000. That is an A series forever. And then you have this 80,000. That we have to basically spread this back over the 10 years, and do that every 10 years will be the same spread. So this is minus 80,000 A given F 10% for 10 years. And then we have this 200,000 that we're going to spread back over an infinite period. So that's going to be plus 200,000 A given F 10% for infinity. And like I said, this A given F is going to be 0. So this is going to go to 0. And we're going to be left with this stuff. And I'll put that on the next page, where I also have the final answer for you. The annual worth, I'll not show it right here, but it'll be in your notes, of this at 10% will be the minus 650 times A given P, 10% for 10 years. I'm sorry, for infinite number of years. So it's just going to be times 0.1. So this is going to be minus 65,000, the first term. And then you have a minus 13,000. And then you have a minus 80,000 times A given F. And that's going to give you $5,020. So that's minus $5,020. And then you're going to have the 200,000 times A given F for infinity, which is 0. So we're going to add these up. That's a plus 200, but that's going to be a plus 0. And this is going to be minus $83,020. So this is minus 78, and 5 is 83, and $20 minus $83,020. And that's the answer that I came up with, okay, for the annual worth of this. The author says to find this annual worth. This is the annual, by the way, this is the annual worth of Z. So let's recap this for a minute. The annual worth of Y at 10% we computed to be minus $74,075. The annual worth of I'm sorry, that was X of Y at 10% we computed to be minus 83,531, and the annual worth of Z was this number. So which is the best alternative? Obviously that would be X. So this is the answer to part A. Now, the question in part B says to use a spreadsheet and find out what the first cost required for each of the two alternatives not selected, so that all the alternatives are equally acceptable. So we're going to make this into a question mark. That's the first cost of this one and the first cost of this one, because we have the best one is this 74. So let's read the question. The first cost required for each of the two alternatives not selected. Well, we selected X, remember, because its annual cost was lowest, $74,075. And now we want to say, well, what would the first cost of Y, B, and Z be in order to have these equivalent? And so I'm basically going to say, okay, so I'm going to take and set the annual cost of X, just to start with at least, which is the 74,075, equal to the annual cost of Y, where the initial cost of Y is unknown. Remember, the cash flow for Y looked like this, minus 400,000 here. Well, we're going to let that be an unknown, minus P sub Y. Okay, and then we had 20,000 a year. That went on for 10 years. And we had a salvage value of 25,000. So that was the cash flow for Y. And so this is an unknown now. And so we'll write the equation again, minus 74,075 equals the annual equivalent of this, and then solve that equation for Y. So this will be P sub Y times A given P, what's the rate? 10%, and this is a 10-year series, minus 20,000 plus 25,000 A given F, 10 and 10. And now we have to solve this equation for this present value. Well, everything is known. This can be looked up in a table or computed and so on. So once we do that, I'm going to get the following. This number, by the way, here, I'll take it one more step, minus 74,075. This is dollars per year. P sub Y times A given P, 10, 10, minus 20,000. And this is going to be a plus. When I spread this back over 10 years, it's only $1,569. And so now I'm going to add 20,000 to both sides. That'll give me 54,000 over here, okay? And then I'm going to subtract this from both sides, and I'll end up with minus 55,644 equals P sub y times this factor. I can look that factor up in the tables, and I get 0.162745. I could also get this from the app simply by putting in P equals 1 and then asking for the value of A given P. If you do that, you'll get this number. And then we need to just multiply both sides through, or divide both sides through by this number, and we'll get P sub y equals this 55,644 divided by 0.162745, and when we do that, we'll get minus 341,909. So in order to make alternative y as good as alternative x, this initial cost must go down from minus 400,000 to minus $300,409. And now you can solve for the present worth of z, this minus 650,000, by setting up the same type of equation for z. Actually, z would be easier because the cash flow for z goes on forever, and if you do that, you'll get minus 560,564, whereas the actual cost was minus 650,000. So that's why it wasn't as good. I'm not going to work that particular part for you. That's the last part, but the answer is there for you to check your work if you choose. Thank you.